Assalamu alaikum wa rahmatullahi wa barakatuh. Alhamdulillah wa salatu wassalamu ala rasulillah amma ba'd. So in the previous video you have seen the configuration of analog to digital converter using PIC18F4580 microcontroller, and the concept of AD control analog to digital conversion was also explained in detail. So in the PIC18F45K80 microcontroller we have a 12-bit analog to digital converter. In the previous version it was a 10-bit ADC module. Now in this version we have a 12-bit ADC module. So there are a few differences here. The first difference that we see here, when we open or when we go to the ADC module in the datasheet, we find that this module now it has AD control 0, 1, 2 registers, and it also has AN control 0 and 1 register. So these registers, AN control 0 and 1 register, these two registers were not there in 18F4580 microcontroller. Now this microcontroller has these two extra registers here. So what is the function of these two registers? So in the previous version, the AD control 1 register was used to configure the AN pins of the microcontroller in analog mode or digital mode. Now in this version, to configure these AN pins in analog mode or digital mode, we do not use the AD control 1 register anymore. Instead of that, now we will be using the AN control 0 and 1 registers. So let us look at the registers here. So we find these registers here. Register 23-8 AN control 0 register. So this is the register which configures the pins in either analog mode or digital mode. So you have several analog pins and you can configure each of them separately and individually. You can configure each of them as a digital pin or an analog pin. So if you write 1 here, that pin will be configured as an analog pin, analog channel, and if you write a 0, that means this pin will be configured as a digital pin. So AN0, AN0, AN1, 2, 3, 4 until 7. Then in the next register we have AN8, 9, 10, 11 until 14. So some of these channels are only implemented in some other microcontrollers. For example, it says here AN 14 to 11 and 7 and 5 are implemented only on 40 and 44 pin ICs and 64 pin ICs. So that depends on how many analog channels you have. So in our case, in this particular microcontroller, so we have up to AN10 here. So AN0, 1, 2, 3, and 4, and 5, 6, 7. Then on this side you have AN8, AN9, AN10. So these are the analog pins which are available and which can be used as analog inputs for this microcontroller, and they can be configured as analog inputs or digital inputs using these two registers, AN control 0 and 1 registers. So each pin can be configured individually as analog input or a digital input. So this is one of the changes here in this microcontroller, in the 18F45K80 microcontroller. Now the other change here is in AD control 0 register. So again, you don't find a big change here. So you only have one extra bit here to select the extra AN channel. So once again, you can use these bits to select any of these analog channels, AN0, 1, 2, 3, 4 until AN10 for the analog input, and to start the ADC conversion. AD on bit is the same to enable the ADC module, and go bit is the same to start the ADC conversion. So before you start ADC conversion, you have to select the proper AN channel using these bits from the AD control 0 register. Now looking at the AD control 1 register, this register is entirely different now, since the analog channel selection has moved to the AN control register. So this register is entirely different now. The AD control 1 register is very different. So here you find the first two bits are special trigger selection bits. So in this case, in this microcontroller, the ADC can be configured to start the ADC conversion based on some triggers inside the microcontroller using the CCP modules or using the timers. So in our case, we are not using it for the time being, so we can simply leave these two bits as zeros, which is the default value. You can see this is the default value of these two bits, so you can leave them as 0. Then the next two bits, these are the V reference plus configuration bits, that means the positive reference voltage configuration bits. So here you have four options here. You can have internal voltage reference 4.1 volt, or internal voltage reference 2 volt, or external reference voltage as the higher reference voltage, or the VDD as the reference voltage. So we will normally use, in most of the applications, we will use VDD as the higher reference voltage. So leave these two bits as 0 once again, so it is default 0 and 0. The negative reference voltage, once again you have external negative reference or the VSS, which is 0 or ground. So leave it as 0 default. Okay, so it says X here, so you can configure it as 0. Clear this bit, make it 0. Then the last three bits are the negative channel selection bits. Now this is a big difference here in 18F45K80 microcontroller. The ADC module can also work as a differential ADC converter. That means it can take two inputs, the positive input and a negative input, and it can find the analog voltage difference between these two inputs. So if you want to use a negative channel or a negative reference input, then you can configure these two bits. Otherwise, these three bits. Otherwise, leave them as 0. Leave them as 0. So it will be VSS, which is the default value. So the comparison will be with respect to VSS, which is ground. So once again, if you look at this register, you can find that we have selected all zeros for all these bits. So 0 0 here, which is default, 0 0 for VDD, 0 for VSS, and again 0 0 for VSS. So this register, you can simply clear this register to clear all the bits and make them zeros. Now let's look at the next register, AD control 2 register. This register is the same, there is no change here. ADFM bit for analog to digital converter result format selection bit. So left justified or right justified. So this is the same bit. Then you can have the acquisition time selection bits. So you can select 60 AD, 40 AD, or 80 AD acquisition time. And then you have ADC clock selection bits. So these are the options here for the clock selection. Now let's look at the table for the clock selection. There is a table given here. So it says here TAD versus device operating frequencies. What is the ADC clock source that you can select? So in this column you can find maximum device frequency. So by default, the 18F45K80 microcontroller runs at 8 MHz clock frequency. So 8 MHz is greater than 5 mega and less than 10 mega. So you select this option, 10 MHz, and this gives you 8 TOSC as the ADC clock frequency. So you'll have to select this option and select ADC clock as 001, 8 TOSC. This is for the default. If you change the clock frequency, then you can change and you can select other options here. So for the default, it is 8 TOSC for 8 MHz microcontroller frequency, and we select 001. So AD control 2 register, these bits we will be selecting 001 here. So we can select left justified, and we can select 4080 and 001 for the 8 MHz clock frequency. Then the remaining procedure is same. After the configuration and selection of the analog channel, simply start ADC conversion by setting go bit and wait for the conversion to complete. And when the conversion is completed, you can copy the data, copy ADC result from AD result high byte, and you can copy it to one of the latch registers, latch B or latch D or latch C. So the important points here in the data sheet, you can find them highlighted in the box like this. See, go done bit should not be set in the same instruction that turns on the ADC module. So that means in one instruction you'll have to enable the ADC module by setting the AD on bit, and the go bit should be set in the next instruction after that. So once again, let us look at the simulation here. So we have connected the LDR, a photoresistor, to AN9, and a thermistor, a temperature sensor, to AN8. So both these are configured as analog inputs. And another important step is to configure RB1 and RB4 as input using the TRIS register. So this step is also important. So whenever we use the ADC module, we must use the TRIS registers to configure them as input, and then we select the AN control registers to configure them as digital inputs or analog inputs. You can find it mentioned here. The analog input channels must have the corresponding TRIS bits selected as an input. So before we start configuring the ADC module, we have to configure the input pins as input and using the TRIS registers, and the output pins as output, once again using the TRIS C and TRIS D registers. So in this simulation, the analog input from the thermistor is taken at AN8, and the ADC module is converting that into digital format and displaying the result on latch D, port D. So you can find, if you change the voltage level here, you can find the output on port D is changing. So it has increased now. Okay, so we have 5 volt here. So you can see this is 5 volt and all the LEDs are switched on. And if you decrease, this is 4 volt, now 3, 2. Okay, and the analog input from the LDR photoresistor is displayed on port C, only the high byte, the higher 8 bits of ADC result from the 12-bit conversion, that is displayed on port C. So at the moment, the input voltage here is 1.6 volt. So this is the equivalent of 1.6 volt, and you can increase it. So now it became 1.7. The input is 1.7, and you can see this is the result. The same way, if you keep on increasing it, the output number here keeps on increasing. So this is how it works. So since it has 12-bit ADC result, so the justification is once again in the same format here. You can either have right justified or we can have left justified, and in our case we are using left justified, and we are simply using the higher 8 bits of this ADC result. So on the breadboard, since we do not have enough space, we have only connected one analog sensor, which is the LDR photoresistor. So this is connected on AN9, So one pin is connected on VDD 5 volt, the other pin connected on AN9, and we have a 5 kilo ohm resistor connected on the same pin, and it is connected to the ground. Okay, and on the output we have connected only port C. In the simulation we had port D for the output of the thermistor, and since we don't have the thermistor here, we have only connected on port C. So port C0 is connected to the LED here, so bit number 0, this will display bit number 0, and you have C1, C2, C3. On the other side you have 4, C5, C6 and C7. C7 is connected here. So each LED is connected with a resistor to the ground. So the anode pin of the LED is connected to the microcontroller side, and the cathode pin is connected to a resistor, and the resistor is connected to the ground. And there is a common ground connected between this breadboard and this breadboard. So you can either use the 330 ohm resistor with the LEDs, or you can use a 1 kilo ohm resistor with the LEDs. The snap connection is same. So power up the microcontroller once you have completed the simulation, and once you see that everything is running fine in the simulation, you get the result. Complete the connection on the breadboard. Complete the connection on the breadboard and download the program using the MPLAB snap. And you will see when you shine a light on this LDR, you can see the number of LEDs lit here, or the ADC result displayed on the LED. That binary number will be a high number, and if you decrease the amount of light on this LDR, then the number displayed here will be a low number or a smaller binary number. Now let us see the working on the actual breadboard now. So this is the actual working on the breadboard. The LDR, you can find it connected here. This is on the AN8 pin of the microcontroller, and a 5 kilo ohm resistor connected to the ground, and the LEDs, they are showing a binary number. So this is the LSB, and here this is second bit. And since we have a lot of light shining here, you can see the number shown on the LEDs is a high number. So if you cover this LED, cover this sensor, if you cover this sensor with something, you can find the number decreases. Now you can find two of the higher MSBs. They have, when I cover, you can find two of the higher MSBs, they have switched off. So if I shine some extra light here on the sensor, the number increases. The number shown on the LEDs, it increases. So once again, let me cover this sensor here, and you can find the number has decreased a lot. And how far it decreases or how far it goes high, that depends on the resistor that you have connected here. So since this is a 5 kilo ohm resistor, so you can find that the number does not decrease to 0. If you change this resistor to a low value, a very low value, then you can find the number decreases a lot more than what you see now. So as the light changes, so it is measuring the light and displaying the equivalent experiment. You can replace this light sensor with a potentiometer, and you can set some voltage divider. You can configure the potentiometer as a voltage divider and measure the voltage and display it on the LEDs. In place of that, you can connect any other analog sensor and you can measure its result on the LEDs. So follow the schematic diagram and download the program using MPLAB snap and complete your activity.